In the desert north of Phoenix, builders poured enough concrete to raise one of the most expensive factories ever constructed on American soil. The price tag now sits past $100 billion, and inside, the machines will carve circuits so small that a single feature measures just a few nanometers across. But there is a strange hole at the center of this triumph. The factory can print a chip. It cannot make the thing the chip is printed on. That thing is a wafer, a thin mirror-polished disk of pure silicon, usually 300 millimeters wide. Every advanced processor on Earth begins as one of these blank circles. The fabs in Arizona will etch billions of transistors onto them. Yet the wafers themselves will arrive on cargo planes from the other side of the world, because almost no one in the United States can make one to the standard these factories require. This is the contradiction nobody puts on the press release. America is building the cathedrals of chipmaking while importing the altar stones. The new fabs solve one stage of a long chain, the printing stage, but the supply line stretches far behind it, and the very first link, the raw, perfect wafer, is barely present on this continent. Solving the visible problem left the invisible one untouched. To understand why, you have to follow the journey of the silicon itself. It starts as quartz rock, dug out of mines, then heated and refined into a metallurgical grade that is still far too dirty for electronics. Getting it pure enough for a chip means removing nearly every stray atom of anything that is not silicon, until the material reaches what the industry calls 9 nines, meaning 99.9999999% pure. Think of it this way. If you scaled a wafer up to the size of a continent, a single misplaced contaminant atom would be like 1 grain of sand out of place across all of North America. At that level of perfection, the silicon is melted and a seed crystal is dipped into the molten pool, then slowly pulled upward while rotating. The atoms line up into one continuous crystal as it rises, forming a tall cylindrical ingot, flawless from top to bottom. That single ingot can stand taller than a person and weigh hundreds of kilograms. It is then sliced into thin discs with wire saws finer than a human hair, and each disc is ground and polished until its surface varies by less than the width of a few atoms. Only then is it a wafer. Every step demands equipment, chemistry, and decades of accumulated craft that very few places on Earth have ever mastered. So who actually mastered it? The answer is startlingly concentrated. A small group of companies, most of them based in Japan, makes the overwhelming majority of the world's advanced silicon wafers. Firms whose names rarely surface in the news supply the blank discs that every leading chipmaker depends on. Between Japan, Taiwan, South Korea, and a few European players, the world's wafer supply runs through a needle's eye. The United States once had a real foothold here. Decades ago, American firms produced significant volumes of silicon for the early computing industry. But as chipmaking spread across the Pacific, the wafer business followed it, chasing the customers, the subsidies, and the dense clusters of suppliers that grew up around the fabs. The expertise drifted overseas quietly, one contract at a time, until almost nothing of scale remained at home. Now the country is trying to reverse that drift, and the difficulty is sobering. Building a fab takes a few years and a mountain of money. Building a wafer plant takes the money too, but it also takes something money cannot rush: the institutional knowledge of how to grow a perfect crystal and polish it to atomic flatness, reliably, millions of times over. That knowledge lives inside the heads and habits of a foreign workforce. There is also the ecosystem problem. A wafer maker does not stand alone. It needs ultra-pure chemicals, specialized gases, precision tooling, and the polishing slurries that finish each surface, all delivered nearby and on schedule. In Japan, those suppliers sit within a short drive of each other, woven together over generations. In Arizona, that web has to be built from almost nothing, supplier by supplier, before the first competitive wafer can roll off the line. This is why the missing wafer matters so much beyond the factory gate. If a conflict, a disaster, or a trade dispute were to choke off the flow of advanced silicon from East Asia, the gleaming new American fabs would have nothing to print on. The $100 billion investment would idle, not because the printers failed, but because the paper ran out. Independence at one stage is not independence at all. There are efforts underway to close the gap. A handful of wafer makers have announced plans to build polishing and even crystal growing operations on American soil, drawn by the same subsidies that lured the fabs. But these projects are early, expensive, and small relative to demand. Even optimistic timelines stretch years into the future, and they will start by handling only the simpler steps while the hardest, the crystal pulling itself, stays mostly abroad. And the wafer is only the first hidden link. Behind it sit the photoresist chemicals, the lithography machines made by a single Dutch company, the rare gases, and dozens of other choke points, each concentrated in one country or one firm. The Arizona project shines a light on just one of them, but it reveals the deeper truth. A modern chip is not made in a place. It is assembled from a chain that wraps the entire planet. So the next time a politician cuts a ribbon at a new chip plant and calls it the dawn of self-sufficiency, remember the blank disk that started it all. The factory in the desert is real, the machines are extraordinary, and the ambition is genuine. But until America can grow and polish its own silicon at scale, the most advanced fabs on the continent will keep printing the future on wafers carried in from somewhere else. The hardest part of making a chip is the part nobody built.
If you found this deep dive valuable, hit the like button, drop a comment below on what tech mystery we should decode next, and subscribe to never miss an episode.